Welcome. We're going to do a little anticipatory activity to get us ready for coordinate proofs. And if you have a ruler and a piece of paper and something to write with, you should have those things at home hopefully, and then go get them and you can do this along with me. And yours should be different than mine, right? Just so that you can see that, yeah, you get the same answer. That there's nothing special about the measurements I chose. Whoops. This ruler is a little hard to use. I assume the values on the left-hand side are supposed to represent centimeters because they're smaller than the values on the right-hand side, which I guess are inches, although they're a lot bigger than that when I look at them. And I'm going to draw a line. So it's a lot easier for you. For me, I'm going to have to use a line tool and try to get it some length that's nice to work with. So I'm just going to start my line there, even though it's not at 0. That's okay. And I'm hoping to get it to an integer value. Oh, pretty close. Just because it's easier for me to find the midpoint, because of course the midpoint is the halfway value. Oh, that looks pretty good. All right, so my line here goes from 2 inches to 12 inches. So the length of that just the absolute value and the differences of those values, because it doesn't matter which way I subtract them if I take the absolute value, because we know that distance is always a positive number. So the length there is 10, which means the midpoint would just be 10 divided by 2, or 5. Right? So now I'm not going to put, of course, a mark on 5, right, because my ruler is not lined up, my line is not lined up at 0. You can line it up easily on 0. I was drawing it way down at the bottom there. But if I come up 5 from the 2, I can do that just as easily, and I'll be halfway. And boy, is it hard to write on that. So you can see if I move the ruler up, I never know what this ruler is going to do for me. So you can see, there we are, halfway at 5. All right, so now I'm going to try to turn this ruler around, or move it around the board, who knows. Come on. No, don't move around the board, turn. When I don't want it to turn, it turns all over the place. Hey, there we go. I don't even know how I did it. And I'm going to draw another line, but the only thing is we have to be on the same units of measurement. Well, I don't have to, but it'd be nice. All right, so the midpoint that I drew, that's going to be the midpoint of my new line. Now I can pick it to be any length I want, so long as I decide 5 will be the midpoint. All right, so for instance, I could choose to start my line at 3. Whoops, no. Or I could see, now I can turn it just fine. But I'd like a line tool, please. I could start my line at 3 and go to 7. Right? So you see 5 would be at the center of that, because that line is 4 units long, and if I divide 4 by 2, I get a midpoint. I get 2, right? The midpoint is at 2. And you can see that it is 2 away. If I make my line long enough, it is 2 away on either side. So I think I'm going to choose that. Now you can make your lines any measurement you want, because the cool thing is it'll be true all the time. So I'm going to give you a little hint. Question 5 is going to be a yes. All right, so now I'm going to connect my points. And actually, let's actually put points there. right, and then we'll connect. And guess what my figure might be? Oh, my one line is maybe a tad not wanting to all meet each other together, but my diagonal there could be, oops. Seriously, I got rid of the line tool. Well, we will leave it there just fine, and we'll get rid of all of these. Sometimes the smartboard doesn't care that I got rid of something. It was happy making lines, so it chose to just keep making lines when all I wanted to do was turn my line a little bit so they could all meet together. There we go. Let's get rid of those. There we go. Yeah, good. All right, so what's this figure? This figure, I hope you know, is a parallelogram. How do we know it's a parallelogram? Well, we made sure that we put the midpoint of this diagonal in the same place as we put the midpoint of this diagonal. Right? So since the midpoint of each diagonal is the same, that's actually should be a comma, not a period. No reason we can't have good grammar here. Both diagonals bisect each other. And we learned that in the lesson on parallelograms. Will this work all of the time? Yes. Right, so parallelograms are quadrilaterals whose diagonals bisect each other, and this can go the other way. Any quadrilateral whose diagonals bisect each other is a parallelogram. So you can be guaranteed that if you have a quadrilateral and both diagonals bisect each other, it has to be a parallelogram. Now it does have to be both, but I put whose diagonals, so that's kind of implying both diagonals. In this lesson, we're going to be doing coordinate proofs, and we will bring back things that we have learned previously, including parallelograms and special parallelograms. So this was just a little introductory activity into coordinate geometry proofs. So there in step 2, the one professor wrote down, then a miracle occurs. I think you should be more explicit here in step 2. Well, we will be very explicit. These proofs are kind of formulaic. They sort of follow a formula depending on what it is we need to prove to show something is true. So coordinate geometry proofs. In the 17th century, the French mathematician René Descartes applied algebraic principles to geometric situations. This blending of algebra and geometry is referred to as analytic geometry. Because this process often involves placing geometric figures in a coordinate plane, it is also more commonly known as coordinate geometry, and that's what we'll call it. We'll call it coordinate geometry. Coordinate geometry proofs employ the use of formulas such as the distance formula, the slope formula, and or the midpoint formula, as well as postulates, theorems, and definitions. So all of our proofs are going to involve some formulas here. And we'll use the distance formula. As a reminder, the distance formula is the difference in the x is the square root of the difference in the x coordinate squared plus the difference in the y coordinate squared. The slope formula, which is the change in the y values, change in y's, over the change in the x values, the change in the run. Midpoint formula, we're just averaging the x values and averaging the y values to find the midpoint. And then Pythagorean theorem we could use in place of the distance formula, or if we want to show that a triangle is or is not a right triangle. Right? And so leg squared plus leg squared equals hypotenuse squared. Right? And you can think of it as x squared plus y squared equals hypotenuse squared. So in this lesson, you'll learn how to prove or disprove that a quadrilateral is a parallelogram, that a quadrilateral is a rectangle, that a quadrilateral is a rhombus, that a quadrilateral is a square, or that a triangle is isosceles or equilateral, or that a triangle is a right triangle. So you can see that some of these will definitely involve different formulas. Right? And we actually have so you're not going to have to like totally think of how am I going to go about doing this proof, because I'm going to show you there's only so many different ways that you can go about doing this proof. So you're going to have all your possibilities listed, and you can choose, unless I tell you to do a proof a certain way, you can choose which pathway you want. But I'll tell you what the pathways are, and we'll do examples of all those pathways. Right? So you can't mess this up. If you're paying attention and you're watching these videos, you can't mess this up. Steps to follow when working on coordinate geometry proofs. So we're going to always do the same steps. First, we're going to draw and label the graph. If the figure has already been graphed for us on the coordinate plane, we can skip this step, but otherwise we will draw and label the graph. We're going to write down the geometric conditions that are required. What do we need to prove? And that's going to depend on which of the pathways you take. Right? So if you want to prove a figure is a quadrilateral, is a parallelogram, there are, I think there's 4 pathways that you can choose from. Right? Once you pick the pathway, that will determine which geometric conditions are required. And sometimes it's just a matter of preference, or sometimes I might ask you to choose a certain pathway. Right? In other words, what is it you need to prove? Because you don't want to find every single thing out about this figure that you're trying to prove as a parallelogram or a rhombus or a rectangle. You want to prove just what you need to prove that it is what you intend to. No less, because otherwise your proof will be incomplete. No more, otherwise you've done extra work. You'll state the formulas that are used, so that would include the distance formula, Pythagorean theorem, midpoint formula, and slope formula. And it may not be all of them, it depends on the problem. You'll show all your work, right? So how you got your answers. You don't have to, it's okay to not show the work on a horizontal or vertical line, but we could still say it's the distance formula, right? Because we could still use the distance formula. It's okay not to show your work on the slope of a horizontal or vertical line, but in essence you were still using the slope formula, you were just doing that in your head. But anything else, you'll show your work. Have a concluding statements showing what you have proved and why it is true. So we're going to do 2 types of proofs. We're going to do paragraph proofs and 2 column proofs. Most of the time I'll let you pick which it is you want to do. I will switch back and forth so you can see both of those. They're very, very similar. So here we're going to look at the formulas, and we're going to do 2 very, very short proofs. We can use slope to show parallel lines and perpendicular lines. Parallel lines have the same slope. So if line AB is parallel to line CD, then the slope of AB, and the slope of AB equals M1, some value, and the slope of CD equals M2, some value, then the only way those lines are parallel is if M1 equals M2, because parallel lines have the same slope. And I think this is all in your notes. Perpendicular lines have slopes that are negative reciprocals of each other. If AB is perpendicular to CD, then the slope of AB is equal to M1, and the slope of CD is equal to M2, then M1 is the negative reciprocal of M2, and m2 is the negative reciprocal of m1. In other words, let's say one line had a slope of 2/3. The perpendicular line would be the reciprocal of that, so they would be switched. Because if I write 1 divided by 2/3, that's the same as 1 times 3/2. And negated, so that'll mean they have the opposite slope. Let's do one more example. So let's say some line has a slope of -4, then the negative reciprocal of that, we would flip it. It's understood there's a 1 in the denominator, and change the sign. So this would be 1/4. Right, so you can recognize that lines are negative reciprocals of one another, right? Or if you're not sure, you can multiply them, because the product of the slopes of two perpendicular lines is going to be equal to -1. So let's see if that's true. So we have 2/3 times -3/2. So 2 times -3 is going to be -6. 2 times 3 is 6, and that reduces to -1. Right? So you can always check it this way. You don't have to, but you can. Let's try it with the other slopes. -4, and I'm just going to put a 1 in the denominator as a placeholder, times 1/4. -4 times 1 is -4. 1 times 4 is 4, and that reduces to -1. So you see, the products of the slopes of two perpendicular lines is always -1. And just a reminder, the slope formula, it's the change in y over the change in x. Make sure it is the change in y. It doesn't matter the order you subtract the y values, right? But make sure once you've picked an order for the y values, you do the same order for the x values. So y2 minus y1 over x2 minus x1, or you can start with the y1 minus y2, but then it has to be x1 minus x2, all right? You have to have 1 point in the first place and 1 point in the second position. So midpoint, we use the midpoint to show that lines bisect each other. So a justification, so if you show using the midpoint formula that two lines have the same midpoint, then you can say that those two lines bisect one another because lines with the same midpoint, excuse me, I should say line segments with the same midpoint bisect each other. Lines don't actually have midpoints because lines are infinite. So what's half of an infinite? Nothing. The midpoint formula, it's you add up the x coordinates, divide by 2, add up the y coordinates, divide by 2. Just the average of the x coordinates, average of the y coordinates. And then for distance, we use the distance formula or Pythagorean theorem to show line segments are equal. Right? So it's the difference in the x coordinate squared plus the difference in the y coordinate squared, and then you take the square root of that, or you simplify the radical if it's not a perfect square. Pythagorean theorem, a squared plus b squared equals c squared, or if you like, x squared plus y squared equals h squared, or leg squared plus leg squared equals hypotenuse squared. Just remember the hypotenuse is opposite the right angle. You can also use Pythagorean theorem to prove that a triangle is a right triangle. Pythagorean theorem holds, it's a right triangle. All right, so here's our little warm-up, and I do think this one is in your note set. The anticipatory set was not, but this one is. We're going to graph AB with coordinates -2, -5. So we'll graph the point -2, -5, and 6, -1. All right, and then I'm going to connect those, and you do the same. I just need a line tool, because who knows what my line will look like on this board. Oops. Well, that was nice, but that's not what I intended. The line tool takes its own sweet time. How about now? Yes. There we go. And I'm just going to label the points A and B. Now let's graph CD. So -1, -1, 3. and then 2, negative 3. Just making sure that I didn't do anything wrong. 6, negative 1, negative 2, negative 5. Okay, everything looks okay. It's easy to look at a number wrong. Am I going to get a line tool? No, I'm going to get a line a dot that moves. Oh, isn't that nice? You should see how far away my finger is from that line, from that dot, and I'm still moving it. How about now? There we go. There we go. So that's C and D. So it looks like D is right on the line AB. Doesn't really matter. But it looks like it. All right, so this was step 1. Step 1 was our graphing. All right, so step 2. All right, so what do we need to prove? Or what do we need to show? We're going to show one of two things, right? So ask us, we're going to find the slope, and we're going to determine the line's parallel or perpendicular. Right? So if we want to show the lines are parallel, we have to show they have the same slope. Show the lines have the same slope. If we want to show the lines are perpendicular, we'll have to show that the lines have slopes that are negative reciprocals. I'm going to abbreviate negative. Step 3, what formula do we need? Well, if we want to prove lines are parallel or perpendicular, we need the slope formula. Right? And so the slope formula is the difference in the y-coordinates divided by the difference in the x-coordinates. Oops, yeah. There we go. All right, so now step 4 is our work. I'm going to move this down a little bit because this is a very short proof. I really don't need this much space. All right, so step 4. All right, we're going to find the slopes. All right, that's going to be our work. All right, so let's find the slope of AB first. All right, and I'm just going to go, from left to right. So negative 5 minus a negative 1. So I'll just call this slope 1. And negative 2 minus 6. That thing is a 1. All right, let's simplify that. So negative 5 minus a negative 1 is negative 5 plus 1. That's going to be negative 4. Negative 2 minus 6, that's like a negative 2 plus a negative 6, that's going to be negative 8, and that would be 1/2. Right, so reduce to lowest terms. Let's do the same thing. Let's find the second slope, right, and that's going to be the slope of CD. So, and I'm just going to go in order. So 3 minus a negative 3 divided by negative 1 minus 2. So negative 3 minus a negative 3 is the same as negative 3 plus 3, 3 minus a negative 3 is the same as 3 plus 3. So that would be 6. Negative 1 minus 2 would be negative 3, and then that reduces to negative 2. Now, if you can look at them and say, okay, 1/2 and negative 2, those are negative reciprocals. If you're not sure, just go ahead and multiply them. And you can see you would get negative 2 over 2, and that reduces to negative 1. So these do have to be perpendicular lines. All right, so this is just an optional way if you weren't sure. So let's do the proof, and you'll see that it's not a very long proof. Our first step, we always start with what we are given. Right? And excuse me. This is, by the way, a two-column proof. We are given that A is negative 2, negative 5. B is 6, negative 1. So we're going to start off with the information that we are told from the proof, told about the diagram. We're given that C is negative 1, 3. D is 2, negative 3. How do we know those points? How did we come up with them? They were given to us. They're right at the top of the page. Step 2, we found the slopes. Right? So we found the slope of AB equals 1/2. We found the slope of CD equals negative 2. How do we find those values? Well, we just use the slope formula. So you see, a lot of times your reasons can be just the formulas you used. Well, what does that mean? If one line's got a slope of 1/2 and the other line has a slope of negative 2, we can say that line AB is perpendicular to line CD. How do we know? Actually, I should probably put the R segments. How do we know that those two lines are perpendicular? Because perpendicular lines have slopes that are negative reciprocals. Right? And that's the end of our proof. Right? The 3 steps. So you see some of our reasons here. You're always going to be given information, and that's probably that's going to be where you start with. You're going to have the work from the formulas you choose. This one we only needed the slope formula because we're just determining whether the lines are parallel or perpendicular. We don't need anything else. And then definitions, postulates, theorems from the first quarter. And that's the end of our proof. See, not so hard. All right, so new points. We're going to graph AB. So A is negative 1, 4. And B is 2, 6. And we should connect those, and hopefully the line tool will want to come out and play. And I won't just move the dots around. All right, there we go. So that is A, B. Right, and then we need CD, so that was 1, 0, and 4, 2. And let's connect with the line tool. All right, so this is step 1. Oh, and I need to label that as CD. And I did label it in the correct order. All right, so step 2. All right, what do we need to prove? What do we need to show? So if they're parallel lines, we have to show they have the same slope. If they're perpendicular lines, there are slopes that are negative reciprocals. So just taking a moment, now this one's of course a very easy proof, but just taking a moment to figure out what you need to show saves you time in the long run. Right? And you can use your notes to figure out what it is you need to show. Step 3, formulas that we need. We need the slope formula. So again, difference in the y coordinates over difference in the x coordinates. Let's show our work. So let's find the slope of AB. So I'll just call it slope 1. All right, and so that is, and I'm going to go in order, 4 minus 6 divided by negative 1 minus 2. All right, so that would be negative 2 divided by negative 3. That's 2/3. We can cancel out those negatives. The second slope, CD there, difference in the y coordinates, 0 minus 2 divided by 1 minus 4. That again would be negative 2 divided by negative 3. And that, after I move these, these steps and reasons here, that would reduce to 2/3 as well. So now that's all we need to write our proof. We start, of course, with the information that we're given. Otherwise, we wouldn't be able to do anything. We're given that A is negative 1, 4, and B is 2, 6. We're also given C is 1, 0, and D is 4, 2. So that is given. Oops, this is a little too low. Okay. Oops. Given. As long as I can write given, I don't care if there's a box around it. There we go. Step number 2. Right? We found the slopes. We found the slope of AB was 2/3. The slope of CD was also 2/3. How do we know that what those slopes were? We used the slope formula. You don't have to make a big sentence of this. You can just write slope formula. These are my slopes. We use a slope formula. And then what does that tell us? It tells us that AB is parallel to CD. We can use the symbol there. And how do we know? We learned in the first quarter, so long ago, that parallel lines have the same slope. So these two lines have the same slope. They must be parallel. And there we go. We're done. All right, so I'm going to end this podcast, this video, and then in the next video, these were just some practice proofs, just proving lines parallel and perpendicular. We're going to do proofs with quadrilaterals and triangles. Right? So see you in the next video. Bye for now.